Hi everyone. So with this video, we're going to be talking about decision trees. Decision trees are another classification tool that you can use, let's say, in contrast to logistic regression. And the main goal of decision trees, or I'll write down it's a classification tool. Right, to assign people to some labels. In our case, again, could be 0, 1, could be A or B, right? And let's say this is someone who gets a loan, someone who doesn't get a loan, no loan. All right, just to stick with the same example we've always been using. And the goal of decision trees is the following, the goal of a decision tree is to segment our predictor space into simpler regions. Now that sounded kind of confusing. So let's just take a toy example and see if we can start to dissect this. You can imagine if I only had two variables, let's just say I only have x1 and x2. And I'll just make this a box. You can imagine that this is actually quite complicated, right? Because it's the entire space, and it's not clear just looking at this how we would, how we would classify, right? So we want to add a little more structure. And what decision trees can do is it can do something like this. It can allow me, and I'll do this in purple. It can allow me to split the space into different regions. Maybe this is one of my regions. Maybe this is another one of my regions. Maybe this is a number here. This is like T2, and I split at T2. Maybe this is T1, and here it splits at T1. And then maybe there's another split here. And then maybe this is T3. It's the same example in the notes, by the way. And then we all split here, and this example is T4. So what have I done here? I've split my space into 5 different regions, right? R1, R2, R3, R4, and R5. And the thinking is now that I have smaller regions, maybe I can classify every observation that lands in this region. So maybe, I'm not saying this is it, but maybe everyone in R1, maybe I assign them, let's say, to class 0, maybe everyone in R3, I assign them to class 1, etc. Something like this, right? And the idea is I'm going to make these regions in such a way that the people who land inside of them are similar. And in such a way that when I, blatantly just assign everyone in those regions to a group, my classification is in some sense good. Usually we don't actually end up drawing it like this. One, because it's, it's quite complicated to do this for anything more than just x1 and x2, right? You can imagine this becomes like 3D and 4D, so I can't really draw it. And people generally like to draw these things not really as dividing a space, but as trees. So I can also draw this region as a tree. So trees generally start at the top, unlike real trees in the real world. And you can imagine everyone starts here, right? And this is maybe the first rule. X1 is less than or equal to T1, right? Maybe this is the first rule that we sort of saw up here in our same predictor space. And then, maybe the tree goes down, right? So we'll say if X1 is less than T1, you go to the right. If it's greater than T1, you go to the left, right? And then if you go to the left, we'll have one more decision to make for you, right? This is maybe X2 is less than or equal to T2. Then maybe this decision here is going to be X1 less than T3. And then this last decision here splits again. And this is going to be X2 less than or equal to, not T2, X2. X2 less than or equal to T4. Right? And this graph, so I'm going to draw a line connecting both of these things. I'll do it in blue. These are equal. Right? These are the exact same representation. Although this tree is really easy to understand, right? So you can imagine that when you have this tree, let's pretend we have it, all you have to do is give me a number, right? So let's say I have a number, let's say the number is 7. Actually, let's give numbers to all of these. Let's say T1, let's say T1 is 10, T2 is 5, this one is 6, and this one is 4. Let's say, right? Now, let's say that our data has two values, x1 and x2. So let's say our data is a new observation. It could be you coming through this tree, right? We're going to have x1 is equal to 4, x2 is equal to 6. Let's say this is our data coming in, and everyone starts at the top, right? So the first thing I do is I check against this condition, and I say, is x1 less than t1? Well, I first reference my x1, and it's 4. And so is x1 less than 10? Yes, it is. Okay, so I go to the left of this tree. Go to the left of the tree. Now I'm going down, and I hit my second rule. Now it says, is x2 less than or equal to 5? Well, x2 is 6 in this case. So actually, it's greater than 5. So I go to the right, and boom, I end at this end node here. Right, and you can imagine for different input data, I would follow a different path on this tree. And so what happens when I hit the end here? Well, at the end, you can imagine I have a lot of observations that fall in each of these boxes, right? And then maybe the way I determine the classification in each of these boxes, again, just kind of like by blatantly assigning everyone the same label. So everyone here maybe is 1, everyone here is 0, maybe everyone here is 1, 1, 0, right? So in this case, my friend who went down this path got assigned to group 0. And that's okay. Right? This makes a lot of sense. So if we assume that we already have the tree, then I think we can all agree this model is very nice and intuitive. Right? All you have to do is look at the data and follow the rules and go all the way down until you hit one of these end blocks. Right? So now, how do we actually determine? So our first question here, first question of the day with these decision trees, we have many, I'm sure. But our first question is going to be, how do we determine the classification? So how do we do this? Well, you can imagine this tree is trained. We train this tree, this model, right? This tree is our model. We train it on our training data, right? So review the validation set video if you don't know what training data means. But we use our training data, right? And you can imagine we have a lot of observations in our training data. And then so you can imagine for any given box, any given one of these boxes at the end, we call these terminal nodes, by the way, if you want to be sure. But for any of these boxes, we have a lot of people in the training data that landed in them. And maybe in this case, we had 4. We had a 1, 1, 1, and 0. Right? That means, because remember again, in these classification problems, our data, we have the true labels, right? We have the true labels, and then we have some data. Right? So when we train our model on this data, I look to see where each data point lands in these end boxes, and then I, again, count the true labels that come with it. And then for each of these boxes, I simply assign the classification. So I assign the label that occurred most frequently. So in this case, what occurred most frequently? Was it a 1 or a 0? Or in this case, in my training data, I noticed I had 3 1s, right, and 1 0. Obviously, 3 1s is greater than 3 is greater than 1. So then this box gets assigned label 1. Right? And that makes sense. And you would repeat this process for all of these terminal nodes. And that's how you would determine which the classifications are. So now, the only other decision sort of you have to make here, right, is, well, I assume that you already had the tree structure, but it's not clear how the algorithm is getting this tree structure for you. So the next question is, how did we get this tree? Well, we got this tree, I'm going to say, in a greedy way. So we got this tree in a greedy way. And so that means at each step, the algorithm is making the choice. So we make the choice that in some sense minimizes classification error. So that means when you have this tree, right, everyone starts at the top of the tree, we make the first split. So this tree is making the split, its very first split here, with a decision that minimizes classification error. So this is the best decision it can make. The best decision it can make to minimize classification error. Now we split the data into two regions, right? Because we have one rule, and now let's say it goes down here and then splits again. Then here maybe it ends. All right, we don't know. And then here again, it looks at a subset of the data and again makes the best decision it can to minimize classification error. And it keeps iterating through this until it can't minimize the classification error anymore, right? So in some sense, it stops for one of two reasons. So it stops when it can't minimize, or more likely what you're going to do is it stops when constraints are met. And this is going to be a loose term in how exactly we're going to get this to work. But you can imagine that having a tree that's too large is not good. So you might have a constraint that says something like don't get too large. So maybe you don't want the number of levels on this tree to get more than like 7 or something like that. That's something you can tell the algorithm to do. And in fact, let's talk about that for a little bit. Why don't you want a huge tree? I'm sure everyone's going to do this. They're going to try and make the biggest tree they possibly can, and they're going to have fantastic classification error. But the issue is you don't want a huge tree. Why? And I'm going to say the biggest reason for us is because of budget constraints. If you have a huge tree, let's say it looks like this, keeps going down and down and down, 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 right, down, 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 down. Right. If it keeps doing this, you have to make sort of a different path or decision for each one of these terminal nodes. And that might be too costly. So I'm going to say this might be too costly. All right, this is hard to do. And in fact, it's very hard to interpret. It's too costly and it's hard to interpret. So actually, a lot of times, smaller trees can be better. Right? Because smaller trees are easy to explain and interpret and implement. So that's awesome. And the only other thing I'm going to mention here is that in Radiance, you can specify the number of levels, right? So you can get a tree that looks about the right shape and length that you can explain. So you can specify the number of levels, right? You can view the plot, and you don't really have to go through any of the math above. Your only steps are going to be you're going to pick what you want to predict. You're going to pick what you want to predict, and then you're going to pick the data, right? And then Radiant's going to produce this tree for you. Okay, so don't worry about that. And your goal, and really this is what I want you to focus on, is interpreting the tree, making sure this tree makes sense, making sure it's easy to explain, right? Making sure it makes business sense, making sure you can make a business decision from it. Right? Like if there's a decision here when you're going down the path that doesn't make sense, I want to know. And make sure you can understand what each of these things are doing. And that's my biggest goal. I really want this class to be interpreting the tree as best as they can. And that, I think, to me, would be a great goal. But don't worry, you are not necessarily computing any of these breaks or anything like that. You will just be observing sort of the outcome of a lot of these things. But interpreting it is very important. And sort of one last thing, I'm leaving this as an aside because I wanted to make sure you understand the algorithm sort of first. But when you split a tree, I said that we minimize classification error. This is not quite true. Classification error is not sensitive enough, but we minimize something that's very close. So we actually end up minimizing this thing called the Gini index. And this is kind of like classification error, but it's a little more sensitive. And this really is it's this proportion. So P1, 1 minus P1, plus P2, 1 minus P2. These are all estimates. And what this is, and in each of the terminal nodes, it's calculating, this is the number of people in class 1, right? This is what these P's are. Oops, put that there. And this is the number of people in class 2, similarly here. And remember, these are for each of those buckets, each of those little buckets at the end of the tree, right? Each of those buckets at the end of the tree. So this is like 1, 1, 1, 0, right? That would mean that P1 is equal to 3 over 4, and P2 is equal to 1 over 4, right? Easy enough. And this Gini index is just a little more sensitive. And it's kind of intuitive, right? Because when P hat is close to 0 or 1, the Gini index is small, which is what you want, which closely mirrors low classification error. I'm never really going to ask you too many questions about this Gini index, but I think it would be useful to know. And alternatively, you might see this thrown around, but again, I'm not really going to test you on it. You might see this idea of entropy, which is similar to the Gini index. Some people prefer it. It's just negative P1 log of P1 minus P2 log of P2 and hats and all these. And again, these P's mean the same thing, and you can imagine this log is doing the same thing as the 1 minus P. So they're very similar, and you might see both of these used when creating trees. So the Gini index and entropy is used to create splits in my tree. And so I know this feels a bit complicated, but again, what I want you to focus on is just understanding how to interpret trees. So if I gave you new data, right, would you be able to understand the path you needed to take in the tree in order to make the classification you wanted? Could you do that? Do you kind of understand how each of the splits are making? Just, how each split in the tree is sort of making a greedy choice to minimize the Gini index or entropy, which again is just classification error. And if you can understand that and you can really interpret the trees that are coming out, then I think you're doing a fantastic job, and obviously implementing it in some sort of software. If you have any questions about this, please let me know.